Hi, my dear students. So today we'll be continuing the circle chapter with next beautiful example. So let us have an example. So for today's example or for today's problem we have if 2 equal chords of a circle intersect within the circle, we need to prove this. So prove that the segment of one chord are equal to the corresponding segments of the other chord. If two equal chords of a circle intersect within the circle, prove that the segments of one chord are equal to the corresponding segment of the other chord. So this is our example for today. So what I do is I'll draw the figure containing the two chords right now. So now this is our circle. It is not beautiful to see, but yet it is good to understand. So as you all know, every circle contains its own origin point or center of the origin, or what center point what we can state it as. Now this circle, as per the problem or as per the question given here, is containing two similar chords. So chord number 1 and this chord number 2. So this is the chord. So let me name this as A, B, C and D. These are the two line segment intersecting each other within the circle. This is as per the problem. What we have to prove is the segment of this particular chord is very much similar to this particular chord. So this is our example actually. Now in order to solve this example, what I'll do is I will draw a perpendicular line with AB, right? So perpendicular to AB, I am joining this line to the center of the circle, number 1, and number 2 I'll be drawing, let me take this center to this part so that I'll get a perfect figure. So perpendicular and no matter the line is very much straight and perfect. Perpendicular to a line perpendicular to AB segment, and similarly I'll draw a line perpendicular to CD. So this is our perpendicular, what I can say, bisector. So I'll get an angle of exact measuring with 90 degrees. Now at this point I will join the line extending from O to, I will end up with the point where these chord meet actually. So I name this point as P. OP is a line joining between the center O to the intersection point of the line segment. Oh, so as you know, I got a triangle. So I'll name this as M, and this particular perpendicular line as N. Now, as for the figure, what I did is, in the solution part, we need to draw OM perpendicular to this part AB, and ON perpendicular to CD first, and this is the second. And third thing what I did is I joined OP. So join OP. Since we have completed the task in order to solve this problem, now what I'll get is, now AM equals to AM equals to MB. It is very much understood that the center is half portion of the total line segment is equal to half of AB. So next, for this line segment, CN equals to ND. So Cn equal to ND, it should be half the portion of the line segment CD, right? So I think you have drawn the figure. For your future reference, I'll be erasing this portion. Okay, so now what I got is, if if AM equals to MB equals to half of AB, and CN equals to ND half of CD, with respect to this I have AM equals to ND. AM equals to ND and MB equals to CN. So reference number 1, because AB is very much equal to CD. Okay. Now, as you know, I got two particular triangles separately. So in triangles OMP and ONP, what I have is we have OM equals to ON, ON equals to ON, and in angle OMP, I'll draw the smaller diagram so that I can explain uh, in a very easy manner. So this is the line segment, another chord or a segment, what I can say, center of the point. And this one I have joined this one, and I have named it as AB, this as CD. I got an angle, I got an angle. I'll name this as O, I'll name this one P. Okay, and this N and this M. Fine. Now in angle OMP, this part OMP is equal to ONP. ONP is equal to ONP. They are very much similar in every angle or every point, right? So therefore OP, as it is a common point between angle ONP and ONP. So we have OP is a common for both of them. So we write it as OP is equal to OP. So this is by RHS criterion of congruence, right? So moving forward, what we do is we must prove that the segment of 1 is most equal to the segment of another chord. So that you should keep in your mind. So now what I'll do is, as per RHS criterion of congruence, triangle OMP is equal to triangle ONP, right? Here MP is equal to PN. MP is equal to PN. It should be equal to PN, and it is equal to PN. So when we add these both, adding 1 and 2, I'll make this as 2, number 1 and number 2. For number 1, what we have is, for number 1 we have AM equals to ND and MB equals to CN. This is number 1. Okay, when we add this number 1 and number 2, we get adding 1 and 2 equations. Can I say it as equation, my dear friends? So adding 1 and 2, I get AM plus AM plus MP equals to ND plus PN. AM plus MP equals to ND and plus PN. Okay. So now when I add this, I'll get an answer. AM plus MP equals to ND plus PN. Okay. I get. So when I add this, I get AP equals to PD. Okay. AP equals to PD. Now subtracting subtracting 2 from 1, we have MB minus MP equals to CN minus PN, where after subtraction I get PB equals to CP. Hence AP 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 is equal to PD and PB PB equals to CP. So thus the point of intersection, or the equal chords of a circle intersected within the circle, when they are intersecting within the circle, we have proved that the segment of one chord is equal to the corresponding segment of the other chord. So we'll see some more beautiful examples in this circle chapter in the next class. Thank you.